How spectra provide evidence that gas atoms have discrete energy level. When atoms de-excite, they emit photons. Photons' energies are quantized. HF, which is energy of photon, equal to the difference between the energy of the two energy levels, E2 minus E1. H frequency corresponds to transition. H frequency in spectrum corresponds to transition between two energy levels. Determine the transition that emits 656 nanometer. Firstly, and as usual, the levels energy are given in electron volt, so we should convert this wavelength to the corresponding energy in electron volt. So we first divided the c speed of light by this wavelength to get the frequency, and then multiply by h, and after that divided by charge of electron to get that energy of photon that represents the transition is 1.9 electron volt. If we continue, we should find 1.9 electron volt is difference between which two energy levels. So cannot be between level 1 or level 1, level 2 or level 1 or any other level. So, and I think it is obvious 3.39 and 1.51 is the answer. And certainly the transition should be from the higher to lower, so from 3 to 2. Number of different photon energies are related to possible transitions. So as this is the energy of the incident photon, we can see that it will make a transition from level 1 to level 4. If you make a subtraction of 13.6 minus 3.39 or this number, or it will only gives the 12 point blah blah electron volt of the incident photon when you subtract 13.6 minus 0.85. So this is the excitation transition. When the electron de-excite from level 4, it can de-excite with the possible transitions listed here. Maybe from level 4 to 1, or to 2, or to 3, or to 3 and after that from 3 to 1, or to 3 and after that to 2, or to 2 and after that to 1. Okay. Note that all these possible transitions are from higher to lower. There is no a reverse direction, no lower to higher, and there is no repetition. You can see that it is 0.2 numbers here, so this can only be measured by micrometer, screw gauge, or digital vernier caliper. To minimize the systematic error, we should check the zero error, take reading while caliper fully closed, and subtract this error, from readings. Because student knows that wire maybe has no uniform cross section. So uncertainty in cross section means we need uncertainty in diameter square, or to add uncertainty in diameter twice or multiply by 2. And to find uncertainty of diameter, we have a range here of measured values, so we can find half the range. This would be the absolute uncertainty. After that, we can divide this absolute with the average value of this range. Note here that we have this value, which is 0.26. It is an anomalous because it is very large compared with the other values. So we got here 6%. Again, for cross section, it will be 12. To find uncertainty in volume, volume is cross section times length. We got the uncertainty in cross section, and we need just uncertainty in length, and certainly the percent uncertainty, because the rule is multiplication quantities that result from multiplication of others needs percent uncertainty to be added, and quantities that result from addition subtraction of others need absolute uncertainty to be added. So here is in length, and for volume it would be the 12 of the cross section plus that of length. Okay, so we have here a thermistor, and this thermistor is connected to a variable resistor that is connected to some light here, and when temperature reaches some value, the light in the duck toy lights off, okay, to inform the child that temperature of the water is now good for him to have a shower. The question here is, if we know that resistance R is set so that VAB is 0.65 volt when temperature is 35 degrees Celsius, we want to calculate this value of R. Okay. Firstly, we should find the thermistor resistance at 37 degrees Celsius. So we'll go for the graph. We have here 36 to 40, which means 4 over 10.04 for very small square, and 0.4 means that we have for 37 two very small squares and half, and go up we can find that this above the 7.5 by half square, half small square, I think, half half very small square. So we expect this R to be I think we can keep it as 7.5 and it is in kilo ohm, so we shouldn't forget to multiply by 10 to 3. Okay, so as we get the resistance of thermistor, and we have both connected in series, total resistance or the sum. Okay, so we can say that EMF equal to the current in circuit multiplied by the sum of R plus the 7.5 kilo ohm. Here is what I did. Okay. I didn't write here R because potential across AB, which is across R, is given, so I wrote this directly and I rearrange it to get I. When I got I dealt by Ohm's law, V equals IR, to find R as V divided by I. And the answer is 2100 ohm. Okay. As R increases, total resistance in circuit increases, I decreases, and VAB will be less than 0.65. Okay, remember that this value at 37 degrees Celsius because I mean this potential at 37 degrees Celsius. Okay, because the current was 3.1 times 10 to minus 4 ampere. When we and the resistance or the variable resistance was 2100. When we change this R, okay, and at also the 37 degree Celsius, we will change I, and as I said, it will decrease if we increase the R. So we expect the potential across the variable resistor R to become less than 0.65. Again, potential across AB or even across the thermistor is current times resistance, and resistance are increased. Okay, so resistance are increased and current decreases. Okay, we cannot use Ohm law to judge whether the potential across AB will increase or decrease by this way. But we can say that as current decrease, the potential across thermistor will decrease because resistance of thermistor remains constant, okay, at 37 degrees Celsius. And as potential across thermistor decreases, potential across AB should increase. Okay, I think there is a mistake here. Okay, let me add some line here and correct this sign. As current decreases, R thermistor constant at 37 degrees Celsius, potential across thermistor decreases, VAB increases, okay, above this value. So light to be on, let me check if this value is a threshold value for light to be on. I think it is. Oh yes, when VAB is greater than 0.65, the indicator light turns on. So VAB will certainly be greater than 0.65, so light will turn on. Okay, so we need VAB to be 0.65 volt, not greater than this threshold value, because we consider this threshold value for light to be on, indicator light to be on, and we need this at the 37 degree Celsius. So if by increasing the resistance of variable resistor R, we have VEB to be greater than 0.65, to bring it back to the threshold voltage, we should increase the resistance of thermistor. Hence, the potential across thermistor will be higher and potential across VEB will return back to 0.65. And how we can make higher our thermistor? We can make it by lowering temperature, because the relation between resistance of thermistor and temperature is inverse relation, as we saw above from the graph. So this value VAB to be smaller, to be back to 0.65 volt, this will be at lower temperature. So the next question, when it asks about benefit of using R instead of fixed resistors, it will be to change threshold temperature at which light is on. Okay, perhaps we want the baby to be in a hotter temperature, hotter water, say 38 or 39, so we can use R. We can decrease R in this case because we want to increase the temperature, so we have to decrease R. and we will have the indicator light to be on at a higher temperature if we decreased R, or lower temperature if we increased R. Part of circuit between A and B must have very high resistance to not affect current in thermistor. Okay, remember that here is the AB and we connect a very high resistance, so current will flow through the variable resistor only and will not go to the branch with the hard opposition to the current. Okay, so not to vary current through the variable resistor. Oh, this should be corrected here to be variable resistor. Okay. We have total resistance of 10 and one of them is 12. Certainly, this is a parallel connection. You cannot have total resistance of 10 and one of the resistor is 12. Okay, the other one, how can we get it? This is the formula, and this kind of same formula in another shape, and we just substitute one of the resistors by 12 and rearrange again, get the other resistor. IV graph for a filament lamp. Total power dissipated can be got from total resistance and potential across the two lamps. Here is we got the potential, so we need to get the R total. As they are identical, R total is R over 2. You can use the formula that we have just seen in the previous question and substitute R1 and R2 by just R and R. You will find that this is correct. So V square over R total means V square over R times 2, which is 2 times B, because B is V square over R. B is the power dissipated in only one lamp. Okay. How can we get this B? Certainly from the graph. We have characteristic graph for one filament lamp. We have the potential set. We can go here, find the current in milliampere, multiply both, B equal IV, and to find B total, it will be this number multiplied by 2. Okay, current in a superconductor is V over R. Voltage across is 0 because there is no resistance for the current, and voltage across the resistor will be just V, okay, because there is no voltage drop across the superconductor. So connection in series here means that potential across the combination is totally go for the resistor and nothing for the superconductor. Okay. We will just add the absolute uncertainties for the two resistors because our total is R1 plus R2. How we get the absolute? We just multiply the percent times the value. Okay. Okay. So we have current equal to potential over total resistance, and as the resistor increased by 15%, so sorry, not the total resistance, I mean current in the second case where the resistance increased by 15%, it becomes 1.15 R, and we have same potential. We can find by calculator that 1 over 1.15 is 0.87. V over R is I, which is the current in the first case before we increase the variable resistor resistance by 15%, and power in second case is V squared over R, which again change it to 1.15. Do same math, you will find okay. Here is a formula for a mass suspended from a spring with some stiffness. Here is the changes that we introduce, 3K, and for M2M we can mathematically manipulate to get the square root of 3 over 2 multiplied by this, which is F on your calculator. Okay. Total distance traveled by point on string in 1 second. So it is not distance traveled by the wave. Someone may say that we have frequency, we have wavelengths, we can get speed. Okay, speed times 1 second get us the distance, but it will be distance traveled by the wave. Here, the question asks about distance traveled by point on a string, which means we will rely on the amplitude value for getting how much distance traveled by a point in 1 second. Okay, during one oscillation, we have two distances traveled, even gradually with time, it will be at the end traveled, which is 4 centimeters above equilibrium and 4 centimeters below equilibrium, which is 8 centimeters. But we shouldn't rush to the answer 8. Why? Because we have frequency, which means 2 oscillation in 1 second. So instead of 8, it should be 16. Sorry, the amplitude here is 3, so it is for one oscillation 6, and for two oscillation it should be 12. That's why we make this 24. I think yes, it goes up gradually and then it goes down again for the equilibrium. So it cuts this 3 centimeter amplitude once up and once down. So this is 6, and after that goes down and again to equilibrium up, so it is another 6. So for one oscillation it is 12, and for two oscillation it is 24. So minimum value between D1 and D2 is delta D, and delta D with respect to wavelength is same as delta phi phase difference with respect to 2 pi. This ratio is equal to this ratio because there is a relation of how to change path difference to phase difference and vice versa. Anyway, we have the two areas, A1 and A2, receiving from some transmitter, okay? And we have frequency, we have the phase difference, so we can plug these values in the formula here after rearrangement, and we can get the answer. I just want to comment that lambda here we got from intuitively from C over F. Okay. Formula for double slit. We will rearrange for Y because we wanted a new fringe spacing. Y2 has distance from slit to screen doubled, and separating spacing between slits also doubled. Okay, so we can see that we return to Y again. Very nice question that focuses on the idea of how power related to number of photons, certainly by multiplying this number by energy of photon over time. Here is the frequency increased, but we have same power, okay? Power is the same. So as frequency increased, number of photons should decrease to make the energy per time the same. And here is the answer. Optical fiber. with core. What difference between times? Taking the shortest path and longest path. For short path we have L over V, and for long path we will also have some distance over V. This distance we can get from cosine theta, because cosine theta is neighbor over the hypotenuse. Okay, suppose we move to here, neighbor over hypotenuse. Neighbor will be the distance of shortest path, okay, which is L here, and hypotenuse we will let it as D. We can rearrange and substitute for T long. After that we can subtract. Here we will find that should be L cosine theta times V minus L over V. Take L over V as a common factor. It will be 1 over cosine theta minus 1. Very well. Okay. Core refractive index should be greater than the clade. Okay. Because we have for refractive index velocity over of light in vacuum or in air over that in medium, and when in core greater than in clad, this means that velocity in core is less than velocity in clad. And for having velocity in core less than that in clad, we can have I less than C for total internal reflection. Anyway, we need the least model dispersion, which means the less time, okay, and we have delta T proportional to L over C times the difference between the ends. So although we need n core to be greater than n clad, we need this difference to be as small as possible. Okay, if we looked here for the choice, we will firstly reject A and C because core, which is Teflon, is 1.4, the least one, so cannot be. For B and C, sapphire has core has a refractive index greater than Teflon, but the difference is not as small as between acrylic and Teflon. So we will certainly choose C. Okay. Purpose of powder coating in fluorescent tube is to absorb one type of particle and emit another. Which one type will be absorbed? It will be the UV, and which will be emitted will be the visible. Okay. Okay, diffraction for beam of electrons with particle duality. What we have here, we decrease the momentum and the number of electrons per second remains the same. What to change for the parabola wavelengths? We have the relation b equal h over lambda. As we decrease b, we increase lambda. And for diameter of the diffraction pattern, it will decrease. Okay, it will, sorry, lambda will increase, means diameter of bright fringe increase. Remember, we have n lambda equal for double slit equal a x over d, this constant spacing, and this distance constant. So as lambda increases, x increases distance between fringes, which means it increases in diameter, even if you use the z for diffraction grating. Okay, this again is constant. As this increases, sine theta increases, and as sine theta increases, this means that theta itself increases and bright fringe increase. Okay, that's all for now. Keep following our channel to see more videos, and for any comment or question, please ask me in comments below. Thank you.